So today I have medium problem. We're given some mass of the planet and we have asteroids, and this represents by their own mass list some numbers, and this is a planet like mass is 4, and we have to answer the question: can all asteroids safely arrive to planet? And if asteroid is less, it can be added to this planet, and if asteroid mass is bigger, then the planet is destroyed. So we have to be careful to choose which order to fly. So solution, the simplest one, just sort, and the smallest one come first, and they would make our planet bigger, and this would allow the bigger asteroids to feel safer. This how it works. It's called greedy, because we only thinking about the current asteroid. We don't do backtracking, and we don't do any choices. We just do our thing within all asteroids in increasing order. Now the interesting solutions. Can we be faster than nlogn? This is a question, because without sorting we have the problem. Imagine we have like 5 at the first asteroid, and the mass of the planet is just 4, and without sorting we have problem, and we can't put this big asteroid, and we have to skip it. However, how should we backtrack to it again? We don't know the heuristic, we don't know any so we can put them in a list, something like that, but will it work in for faster than n squared? Okay, now let's look at the math solutions for this problem. It's the first interesting problem, first interesting solution. So imagine we have numbers like 2, 4, 8, and look at the binary representation. This 1 0 1 0 0 and 1 0 0 0. Imagine we have some numbers like 3, it is 1 1, and maybe 5, it is 1 0 1, and our planet is just 4. So we can put all these numbers, but we can't put 5. And if we look at the first leading bit, like we have number 4, number 5, as they have all the same first bit, highest bit, like that. Imagine number 6, it is also in the same group, and number 7 also the same group. All have the same leading highest one bit set at position 3, and that means if we add just smallest of this group, the smallest is 4, if we add to any to any of this number if we add just this bit, so plus, we immediately became bigger than any of these numbers. And that means, so add smallest, planet is saved. Planet is saved. This is how it works, this is how it looks. This is our planet. And if we add the smallest asteroid from the group, like 4, and our planet is also 4 by the way, and he flies here, and that means this bit allows to all the other numbers, all other asteroids from this group of the same highest one bit to be safely placed on the planet. And that means we can group by highest bit, because adding the smallest allows all the group to arrive at the planet. This is how it works. So basically what we're doing is we iterating over all 32 bits like this, and for each bit we can start with smallest, and in this group we iterating over our asteroids and filtering all the numbers that have this position of the highest one bit, and then we take in the minimum of it and add into the planet, to the mass. Okay, I shouldn't write it like that. Mass. So or we can do separate step of iterating over asteroids, grouping by bits in some array, and have 2 variables inside for each bit, like minimum and sum, these 2 variables. And then we taking our planet, taking our bits in order. If the minimum is less or equal the planet, we can take entire group. This is the solution, and it is all of 1 space complexity, because we only have to store 32 numbers of I64 bits, and time complexity of n, because we only scan this asteroids once, and this is enough. Now this is the first interesting solution, and the second solution in the same interesting group is quickselect. And I will describe it like that. So imagine we have some numbers 5, 4, 1, 2, and we have our planet size of 4, and the quickselect is we just take our planet size as a measure, and we do shifting all the positions that are less or equal to the first spot. So scanning, and this is skip, then we see 4 swaps with 5, then we see 1 swaps with 5, and we have 2 swaps with 5, and this is the final step of the quickselect, and this entire prefix is consumed because it is less than the mass, and we take in the tail to the next phase. And how many phases we have? How many phases of quickselect we have? And this is the same mathematical proof that we don't have more than 32 phases. Why? Because of the same property of doubling bits. So imagine we have mass, some mass at this position, and we have next that should be 2 times mass, and this next would be how much? 4 times mass, and so on. So it is 2 times power of k sequence, and it will grow very fast, because if we have 10 to the power of 5 asteroids, we can't take this much growth. Eventually we have logarithm 2 steps at most. So this is a solution, and by the way, this is the fastest solution that I achieved in Rust. And let's look at the code. This is my accepted version. I just use simple sort, then scan. This is not interesting. Now let's look at other code. So this was the Rust quickselect solution. We have some pointer to the start of the array, and we have inner loop that does swapping, does a swap, and it compares to the current mass. This is how you take in this, instead of the standard quick select in a quick sort is taking some medium or middle, but in this we have mass, and this is our heuristic. And after we don't even compare the masses anymore. We just look if our index is shifted, so have it take anything. If it's not, we stop. Now let's look at the Kotlin version. This is a shortest variant, not very interesting but very short. Now let's look at Rust binary solution. So this is a bits, it's the sum and minimum and sum, 32 values per bit group, and then we do scan once, and we do calculate the minimum and sum per bit group, and then we do this scan from lower to higher bit, which comparing this minimum. If we can take it, we do take it, and if not, then we done. So this is a 4 milliseconds, and this quick select solution just 1 millisecond, and I even got 0 milliseconds, but the code was blocked, so I wouldn't publish that, so I prefer this 1 millisecond. It is shorter. So that's it for today.